Welcome to the Chapter 9 Part 2 video where we're looking at the binomial theorem. Now, we already started investigating and kind of digging into the binomial theorem in class during our Chapter 9 introduction. And we're just going to kind of take that one step further and look at a variety of binomials and apply the binomial theorem to that. Okay, so what we're going to look at, powers of binomials, is a review. Pascal's triangle is a review. The binomial theorem that we're going to formally state, and then a couple of factorial identities. The binomial theorem is a marvelous study in combinatorial patterns. This is a super intricate and interesting way of applying the combinations that we learned in the last section in a practical way. There are so many times that we have to add something together and then raise it to a power, whether it is complex number or irrational numbers. That comes up so often in physics and engineering and just all different areas of study. A lot of them technical related. I don't know as much if it would come up in non-technical fields, but this comes up all the time in technical fields. So we're going to start out by looking at powers of binomials. Now, we already derived all of these in class, so I'm not going to redo all of that. I don't want to whiteboard. There we go. So powers of binomials, what we have to remember is to distribute do not make the donut mistake. The donut mistake is when I have something like a plus b squared and I don't distribute. If I just say, oh, well, that's a squared plus b squared, and I forget about the 2ab, then I've forgotten the center to my donut. So my donut has a hole. Okay, so we have to distribute for any time we're raising more than one term to a power. So whether it's a binomial or a trinomial, or as long as it's not just one term, I always need to distribute. Okay, and then we started saying that the pattern that we're going to look for is among the coefficients, and then separately we're going to look at the powers of a, and then separately we're going to look at the powers of b, and we're going to tie all of those together into a single pattern, and that pattern is called the binomial theorem. And we kind of went through this whole pattern two classes ago when we introduced the chapter. Okay, so if I'm looking at these coefficients, I have a plus b to the 0 equals 1. A plus b to the first is 1a to the first b to the 0 plus 1a to the 0b to the first. And we can write that in a much simpler way, right? We can just write that as a plus b, but then we won't be able to see the pattern as clearly. Same thing for our next line. We could write that as just a squared plus 2ab plus b squared, but it will be a little bit harder to see the pattern if we simplify our terms. And that pattern that we're looking for, let's start by just looking at the coefficients. The pattern with the coefficients is that it's making this kind of expanding triangle. In last class or 2 classes ago, we said that that was Pascal's triangle. And I'll put Pascal's triangle back on screen so that we can see it and we can test some values in it. But there's a shortcut, a more direct way to find these values that are our coefficients. And that is to use the combinations that we saw in our section 1 video. Now, combinations are essentially looking at a group of objects and saying, how many different ways can I choose some of them? So if I have 10 pens and I want to choose 5 of them to do my coloring project, how many different sets of 5 colors could I choose, right? That's a combination, because it doesn't matter which order I choose those colors in, they're all going to be used in my project. So how that relates to binomials is that when I'm distributing, I distribute a and b to every term. And so the pattern of that distribution follows the pattern of choosing objects. So we're going to look at it as choosing objects from a set of 0, choosing objects from a set of 1, choosing objects from a set of 2, and those numbers are coming from our exponents, choosing objects from a set of 3, choosing objects from a set of 4, choosing objects from a set of 5, and so on. Okay, so let's look at just the case of the a plus b to the 5th. If I have a plus b to the 5th, those coefficients 1, 5, 10, 10, 5, 1 follow the pattern of choosing from 5 objects each of our whole numbers. Now, whole numbers means I'm starting at 0. Notice we started our table with an exponent of 0. We're going to start our choosing from an exponent of 0 too. So if I choose 0 out of 5, well, there's only one way to do that. I choose none of them. If I choose one item out of 5, there are 5 ways to do that, because I can choose the first one, the second one, the third one, the fourth one, or the 5th one. Once I choose 2, now I have a lot more options, right? So if I'm choosing 2 objects, I could choose any of the 5, and then I could choose any of the 4, and then we might say, oh, well, there's 20 ways, but whether I choose red and blue or blue and red is the same. So we have to then divide that by 2. So we get 10 ways to choose 2. Your calculator does this as well. The way I would do that in my calculator is 5, choose 2, or 5, NCR 2, right? So then we say, okay, well, then how many ways is there to choose 3? And the interesting thing about the choose function is whether I choose to use those markers or not use those markers is the same. So choosing to use 2 markers is actually the same number of choices as choosing to use 3 markers, because if I'm using 2 markers, then I'm not using 3 markers. And that's the same number of choices. Then we can choose 4 of them, which is the same as choosing not to use 1 of them. And then we can use all 5, and there's only one way to choose all 5. And so we can see this pattern that our coefficients are following this choose pattern. So let's look at this formally. The binomial coefficients that appear in the expansion of our a plus b to the n are the values of n choose r, for r equals starting from 0. This is the one that we sometimes forget. If you forget your 0, you'll be off by 1 coefficient. You'll probably notice, because you know you always start and end with 1. The classic notation for n choose r, a lot of times we use this kind of parenthesis notation, n in top, r in the bottom. So this is the same n and r that we can use in our calculator, n choose r. Equally, there's no difference in their meaning. N choose r, you don't say it differently, you don't calculate it differently, it's just a different way to write it. Okay, so let's look at an example. In this example, we have a plus b to the 4th power. Now, without using your previous notes, we're going to try to expand this. Okay, and we can use our calculator to calculate the coefficients. I might just do them in my head because 4 is not too big of a number. So we're going to start out, our exponent is 4, n equals 4. Okay, then I'm going to say that a equals a. I know this is a little redundant. B equals b. The reason I'm going to do that is because sometimes our binomial will not just be a plus b. So I like to do this vertically. I'm going to set it up. 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, 4, choose 4. And then I'm going to go ahead and fill in my variables at the same time. So a was my first term. I'm going to start with a to the 4th, a to the 3rd, a to the 2nd, a to the 1st. I'll write a to the 0, but we know that that just equals 1. And then we can do our b's, starting with the 0 to the 1st, to the 2nd, to the 3rd, to the 4th. Now, you may have noticed those exponents always add up to 4. This is a good check to make sure that I didn't accidentally go up instead of down or down instead of up. all of those exponents should add up to 4. So 4 plus 0, 3 plus 1, 2 plus 2, 1 plus 3, 0 plus 4, we're okay. Now we're going to do the calculation part. If I have 4 objects and I choose none of them, there's only one way to do that. That's 1a to the 4th, b to the 0 is just 1. If I have 4 objects and I'm choosing one of them, there are 4 ways to do that. A cubed b, I don't need to write to the first. If I have 4 objects and I'm choosing 2 of them, I might say that's 4 times 3, but again, red, blue is the same as blue, red, so I have to divide that by 2. So that is 6. A squared, b squared. If you're not comfortable calculating these in your head, absolutely, you can use your calculator, and I'll show you a little bit of a shortcut as well. 4 choose 3 is the same as not choosing 1, so that is 4ab cubed. 4 choose 4 is the same as choosing none, so that is one way. I don't have to write a to the 0, b to the 4th. And then I add all of them up. So I have a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. And that is our expanded form. Okay, now if you are deciding to use your calculator in order to calculate all of these, there's a little shortcut that you can use. Is it easier? I don't know. Is it fewer calculations? Yes. Okay, so when you're doing this, if you want to calculate all of those at the same time, in your calculator, you can do 4 and choose R and then do a set. And you can take 4, choose each of the numbers in the set. Now, the curly brackets are right above the parentheses. So you're going to do second parentheses. So if you look at 8 and you look just above the 8, you have the parenthesis button, and above the parenthesis button is the bracket button. So you can do 0, 1, 2, 3, 4. And then if you hit enter, that will give you 1, 4, 6, 4, 1. And those are your coefficients. Depending on your calculator, it might cut off. Then you have to hit the arrow before you type anything else. So don't hit enter again or anything like that. As soon as it gives you the answer, hit the right arrow and it will start to scroll. Okay. If you have specific calculator questions on those, we can go over those individually. If you're looking for the comma button, comma is just above the 7. There's no indication that it's a comma and not an apostrophe. So if you're looking at it and you're saying, oh, that looks like an apostrophe, you're looking at the comma. There's no apostrophe, just the comma. I shouldn't say there's no apostrophe. There is an apostrophe, but it's in a menu. Okay, so that's kind of a little bit of a shortcut. If you're doing longer, bigger values and you want a longer set, you can really get rid of the first and second one because you already know that those will just be 1. Right, so we know that those end ones are going to be 1. So if you know that, then there are fewer numbers to look at on your screen. Okay, that's only if you wanted to use your calculator for it. Really, if you're using your calculator and you're really just calculating one value, it's not worth typing the whole set in there. Okay. So that's expanding the form. I told you I would show you Pascal's triangle. So as a reminder, these coefficients form Pascal's triangle. There are so many patterns. A couple of the ones that we talked about in class are that the outside is always 1s. The second diagonal is the counting numbers. So we're just going up by 1, and that goes both ways. The next diagonal is the triangular numbers. So we're adding the next consecutive number. So we said that's +2, +3, +4 going down. But we said we can also see that by adding these little triangles together, 4 and 6. So that means 5 and 10 is 15. The triangles will also help you fill in any other blanks. So we know that middle number is 20. We said there's symmetry. It's 1, 6, 15, 20, 15, 6, 1. And we know there will be a middle number when the row above it did not have a middle number. We can also say that if this is row 6, there are going to be 7 terms. Every row has one more term than its row number. So if my exponent is 9, I can expect 10 terms. Okay, those are just some of the patterns in Pascal's triangle. I mentioned in class, there are so many patterns that you could just have a full weekend of just finding and researching patterns in Pascal's triangle, and you still wouldn't look through all of them. Okay, so let's go ahead and formally state the binomial theorem. The binomial theorem states that a plus b to the n is equal to our coefficients, which were n choose all the numbers from 0 to n, times a to the n times b to the, we can say, n minus r. All the way up to b to the n. Okay, so essentially, the way that we can write this is we can say that we're adding up all of the terms. Now, there's a special notation that I'm going to introduce you to, and it means a summation. This is a Greek letter, sigma. It is a Greek letter, and this is the capital version of sigma. And what it means is add up everything. So we can say add up every n choose r times a to the n minus r times b to the r. So that means when r is 0, we have n choose 0, a to the n minus 0, b to the 0, right? When r is 1, n choose 1, a to the n minus 1, b to the 1. So we're substituting values of r. And we're going to start substituting at 0, and we're going to stop substituting at n. This is a very fancy notation. This is called summation notation. Okay, summation notation. So we're going to see that more in the next section as well, when we're looking at series and we start adding up sequences, patterns. But I wanted to introduce it here so that we can kind of be familiar with it before we start getting into more complicated series. So in this case, we're adding up. We have our choose value, that's our coefficient. And then we have our powers of A. And lastly, we have our powers of B. Okay, that's the binomial theorem. You don't have to know the summation notation, but you should be able to recognize what each part of it means. We're going to get more into detail with that in the next lesson. Okay, so let's look at one more example. Expand this. Now it will make more sense why I had labeled A equals and B equals on our previous example. I'm going to start out by saying our exponent is 5. Now our A is z cubed. Our first term is z cubed. Our B is 5x squared. That's our second term. If it had been subtraction, my B would be negative, right? And now I'm going to set up my terms. And this is why I like to line them up vertically, is because now I can have as much space as I need horizontally to solve each term individually. I don't have to rewrite the entire expression every time I simplify a term. And then I can add all of them up at the end. So starting at the top, 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. Let me make my 3 more clearly a 3. Okay. There's my coefficients. Now my powers of A. I have z cubed, which is just the A, raised to the 5th power. A to the 4th. A to the 3rd. A to the 2nd. A to the 1st. And then I'm not even going to write it because I know that's just going to be 1. So I'm not going to write A to the 0. I start out with B to the 0. Now I have B to the 1st, B to the second, b to the third, b to the fourth, b to the fifth. Whew. Now we've written the kind of raw form of each term. I'm going to start simplifying. 5 choose 0 is 1. Z cubed to the fifth. Now remember that means z cubed times z cubed times z cubed times z cubed. Whoops, I'm doing it in the address bar. Hold on, let me rewrite that. Z cubed times z cubed times z cubed, 3, 4, 5. So if I add all of those exponents, this is z to the 3 times 5. Just a little review of exponent rules there. So this is z to the 15. So that means my first term is just z to the 15. Now, why is that exponent larger than 5? Because our term had an exponent of its own. It's our original exponents, 5 and 0, that add up to 5. 4 and 1, 3 and 2, 2 and 3, 1 and 4, not the solution that has to add up to 5. Our next term, 5 choose 1 is 5. Z to the 3 times 4 is 12 times 5x squared. 5 times 5 is 25. Z to the 12th x squared. You can put those in alphabetical order if you'd like. Since all of them are going to have z first, I'm just going to leave z as my first coefficient. 5 choose 2 is 10. Z to the 9th times, now that's 5 squared. So that's 25 x to the 4th. That's 250 z to the 9th x to the 4th. So really all I'm doing is I'm simplifying, but I'm being very careful about those exponent rules. Okay, 5 choose 3, also 10. Z now to the 6th. 5 cubed is 125. X to the 6th. 125 times 10 is 1,250. Z to the 6th, x to the 6th. Okay. 5 choose 4 is 5. Z cubed times 5 to the 4th. That is 625. X squared to the 4th is x to the 8th. 625 times 5. I'm not going to try doing that in my head. I'm going to verify it on a calculator. 3125 z to the 3rd x to the 8th. 5 choose 5 is 1 times 1 times 5 to the 5th, which is really what we just calculated when we did 5 to the 4th times 5. So that's 3125 x to the 10th. You can verify it on your calculator. Absolutely. 5 to the 5th is 3,125. Okay. Now we're going to add all of these up. So really what we're doing here is we're finding the summation of 5 choose r z cubed to the n minus r 5x squared to the r from r equals 0 to 5. And that equals adding up all of my terms. So I'm going to go through and just circle my final term for all of these. That was z to the 15th, 25, z to the 12th x squared, 250, z to the 9th x to the 4th, and so on. And then I'm going to copy them down here. Z to the 15th plus 25z to the 12th x squared plus 250 z to the 9th x to the 4th plus 1250 z to the 6th x to the 6th plus 3125 z cubed x to the 8th plus 3125 x to the 10th. And that's all of them. So this was x to the 5th. I have 6 terms, 1, 2, 3, and then 3, 4, 5, 6. Yep, I've got all 6 terms. It's a good check to make at the end to make sure I didn't skip anything. Okay, so that is the binomial theorem. Okay, that's the last practice problem we have. The last slide that we have is just factorial identities. This is the first time we're really using factorials a lot. So factorials, I can always rewrite n factorial as n times n minus 1 factorial, right? Because n minus 1 will keep going down to all the way to 1. And then I can also write in the same thought process, n plus 1 factorial is n plus 1 times n factorial. The only difference between these identities is that for n factorial, we're starting at 1 and greater. We are not looking at 0 factorial because 0 factorial equals 1. And for n plus 1 factorial, then we can have an n value of 0. Okay, that is it for today's video. I will see you in class.